You know, everyone is obsessed with GPUs. We talk about them like they're the roaring engines of the whole AI revolution. But what if I told you the most important part of that engine isn't the part that makes all the noise, but the one that's quietly feeding it? What if we've been looking at the wrong thing this whole time?
I mean, you hear quotes like this from guys like Sam Altman, and it just reinforces that idea, right? That the AI boom is all about the GPU. We think of them as these super intelligent, totally overworked brains doing all the heavy lifting. And look, in a way, that's true. But it is absolutely not the whole story.
Because here's the crazy part. According to Professor Kim Jung-ho, one of the literal founding fathers of this tech, the GPU spends a surprising amount of its time, well, just waiting. Yep, just sitting there, idle, twiddling its digital thumbs. So that begs a really fascinating question. If the all-powerful GPU is just waiting, what on earth is it waiting for?
Okay, let's dive into this. And there's a brilliant analogy that makes it all click. I want you to imagine your AI system is a super high-end restaurant. The GPU, that's your star chef, a genius who can cook any dish you ask for almost instantly. But a chef, no matter how brilliant, can't cook without ingredients.
And that's where the server comes in. In our AI kitchen, the server is something called high-bandwidth memory, or HBM. And this poor server is just frantically running back and forth, trying to bring ingredients from the pantry to the chef through this tiny, narrow hallway. So here's the key takeaway. While the chef gets all the glory, the server, the HBM, is the real bottleneck. The whole restaurant can only move as fast as that server can deliver the data.
So the solution to this delivery problem was HBM. It was a genius idea. Instead of spreading all the memory chips out horizontally, engineers thought, hey, what if we go vertical? They started stacking them, creating what is basically a memory skyscraper right next to the GPU. This makes that hallway super short and super wide, allowing for a massive increase in data transfer. It's really an incredible piece of 3D engineering.
All right, so we've got our memory skyscraper. Sounds great, right? Problem solved. Well, not quite. As anyone who's ever built a real skyscraper knows, building up creates a whole new and frankly much harder set of problems. You can't just pile things on top of each other and call it a day. You need some seriously complex infrastructure to make the whole thing work.
So building one of these things is a mind-boggling process. First, you stack the memory chips, floor by floor. Then, and this is the wild part, you have to drill thousands of microscopic holes, called through-silicon vias, or TSVs, straight through the entire stack. These are the building's elevators, whisking data up and down between floors at unbelievable speeds. Then, you place this whole skyscraper city right next door to the GPU.
And just like in a real city, when you pack that much activity into such a small space, you get enormous problems. First, you got to get power to every single floor of that skyscraper, and it has to be perfectly stable. But the bigger, more immediate villain, the one that keeps engineers up at night, is heat. All that action creates a massive thermal crisis.
Remember our star chef, the GPU? Well, it runs incredibly hot. We're talking over 100 degrees Celsius, hotter than boiling water. And since that HBM skyscraper is built right next door, all that intense heat just bleeds over, cooking the delicate memory chips. And when memory gets too hot, it starts making mistakes, dropping data, which can crash the entire system.
What's so interesting here is this chain reaction. A hotter GPU means a hotter HBM, which directly and dramatically increases the risk of these catastrophic data errors. This one problem has kicked off a frantic, high-stakes arms race to find new ways to cool these systems down before they literally melt themselves.
And this timeline just shows you how extreme things are getting. Right now, we use liquid cooling, basically running tiny water pipes over the chip. But guess what? That's not going to be enough for much longer. The next step is immersion cooling, literally dunking the entire computer into a bath of special non-conductive fluid. And looking even further out, engineers are planning to build cooling pipes directly inside the silicon itself. It's wild.
So, if cooling today's AI, which is mostly text-based, is this hard, what happens next? Because the future of AI isn't just about text. It's about generating high-resolution video on demand. Think about asking an AI, hey, create a 1-hour photorealistic movie for me, and having it done in a minute. To make that kind of leap, from text to video, we're going to need systems with about 1,000 times more memory capacity and 1,000 times more bandwidth than what we have today. 1,000! Simply building our HBM skyscraper a few floors taller just isn't going to cut it. We need a totally new approach. And this is where the next revolution is poised to happen. HBF, or High Bandwidth Flash. The idea is to build another skyscraper right next to the GPU, but this one is built using flash memory, the same kind of dense, high-capacity storage you've got in your phone's memory or in a solid-state drive.
The best way to think about this is with one more analogy. The HBM skyscraper, that's the AI's immediate workspace. Think of it like a desk where it does its active thinking. It's incredibly fast, but it's relatively small. HBF, this new building, is the giant library next door. It holds the AI's entire collective knowledge, every book, every picture, every piece of data it has ever learned from. It's absolutely massive, and it's right there, instantly accessible. Now, the introduction of this library concept is way more than just a simple upgrade. It actually signals a fundamental, ground-up shift in the entire philosophy of how we build computers for AI.
So what does this all mean? Well, for starters, we are moving away from a purely GPU-centric world, where all that really mattered was the speed of the chef. We are now entering a memory-centric era, where the size of the library and the efficiency of the entire kitchen are what's most important. Suddenly, cooling technology is just as critical as raw processing speed. And the companies that master these incredibly complex memory and cooling systems, they're going to hold enormous power.
And that leaves us with one last, really critical question. For decades, power in the tech world belonged to the companies that made the fastest processors. But if the real bottleneck and the key to the future is actually memory, we have to ask ourselves, in the next chapter of AI, who really runs the show?